one, and we are making a significant shift in how we're looking at functions and relating them to calculus, starting with this unit. So today we're talking about exploring accumulations of change. So an accumulation is a lot like something like snow accumulating, right? It's something that tends to just kind of pile on time after time after time. So our central question is, how is accumulation of change represented? So how are we going to see this when we're looking at functions and at problems? So until now, you've been presented with functions and asked to determine information about the rates of change. In other words, I give you f of x and I have you tell me about f prime of x. And that has been the focus for pretty much the entire year up until today. In this unit, we're going to reverse that process. So what does that mean? That means we are going to present you with a rate of change. So we are going to give you the derivative, and we're going to ask you to recover some information about the function whose rate of change we know. So think of it as kind of like, I know what f prime is. Now I have to tell you about f. And we did a little bit of that graphically. In this note session, we're going to really look at it in terms of a contextual application. So we're going to start with this application here. It's a velocity problem, and it's something I think you have some decent familiarity with. Truck travels along a highway at a constant velocity of 60 miles per hour. And they travels that for 2.5 hours. How far did it go? Now, we don't need calculus to answer this question, but we can use calculus. And so when we think about this, if we have this rate, right, we're talking about presenting you with a rate of change. Here's the rate of change, 60 miles per hour. And we're being asked for you to recover information about the function. So we know velocity is a rate of change. It's the first derivative of position. So I have the rate of change. I'm asking you something about position. How far did we go? How far away are we? That sort of thing. So if you think about this just logically, intuitively, right? If we travel, we know that we can recover information about how far we've traveled if we know about a rate. So we know that if we know how fast we're going, for how long, we can recover things about position. And so just intuitively thinking, if we're going at 60 miles per hour for an hour, we know we're 60 miles away. Okay, so we could actually build out to 2.5 hours without using any calculus. And that's kind of what we're going to do today. We're not really going to use any calculus. So let's represent the rate of change graphically. So I've got a grid here. I'm labeling the grid 1, 2, 3, 4 boxes out as an hour, 8 boxes out as 2 hours. That way we can get to 2.5 all the way to the end. I'm going to arbitrarily call each box 10 on the vertical axis. So here's 30, here's 60. Let's get some labels on the axis. So we have time in hours, and we have velocity in miles per hour. And then so we know if we're traveling along a highway at a constant velocity, that means we're always going to be at 60. And that means we are going to have basically a horizontal function. Okay. And so when we look at this, we want to cut it there after 2.5 hours. Okay, well, if we look at this intuitively, if we go out an hour, we should have accumulated 60 miles of displacement or 60 miles of distance. So when we look at that graphically, we can see that this green rectangle here is a width of 1, a height of 60, its area is 60. And it's no coincidence that that's also how far we've traveled in an hour. Well, let's go out 2 hours, right? In the next hour, we travel another 60 miles. So in total, if we add up these two areas, we've traveled 120 miles. If we look at this geometrically, we see that we have a rectangle. I'm going to combine the red and the green. We get a width of 2 and a height of 60. There's your 120 miles. But we're not done with the trip yet. We go out another half an hour. And we know if we go out another half an hour, we've traveled half this distance. So there's your final half hour of travel. It's got a width of 0.5 and a height of 60, so it's another 30 miles. So in this case, we can simplify this. I didn't have to divide it up as meticulously as I did, but we can look at this then as the distance traveled is really boiling down to a geometric shape. And the geometric shape is under the velocity or under the rate of change graph. So this distance then is the base. The base of this geometric shape is 2.5. And I put in hours because we want to be really cognizant of the units here, because that gives us our contextual information. And then its height is 60. And again, I put the units in miles per hour. And so we know if we take base times height, we can get the area. So 2.5 times 60 is 150. And then to work with the units here, we think about this, we're multiplying two numbers. And our units here, our hours are going to cancel, right? In other words, if you think about what we're trying to accomplish here, right? We're presented with a rate of change and asked to recover information about the function whose rate of change we know. So this is my rate of change, and this calculation is recovering the information that we need about our change in position. Or in this case, I asked it as how far did I travel? And so those hours, our units of hours cancel, and we're left with units of miles. Okay, so the idea here is that, again, we're presented with the rate of change. We have this velocity function, and we're recovering information about our position. Okay, and our velocity is a rate, and underneath the graph of this rate ends up being information about the original function that we wanted to recover. Let's change the question a little bit. Let's have that truck now slowing down over a 10-second interval as it approaches an off-ramp. Okay, so let's get this let's get this information on the graph here. So we get a 10-second interval. So I'm going to use each box as a second. And I'm going to just arbitrarily say, based on the last problem, we started at 60. Let's say we slow down to 40. So if we start at 60 and slow down to 40, let's get the labels on our axes again. We've got time in seconds, right? 10-second interval. We've got velocity in miles per hour. We have a mismatch in these units. We'll take care of that eventually. But we have hours and seconds. So we gotta convert one or do something. I can show you kind of a slick way of doing that. Okay, so let's say we start at 60 miles per hour and we slow down to 40 miles per hour as we approach the on-ramp. So the question is, how far did it travel during that time when it was slowing down? So again, we've been given information about the rate of change, and we're asked to recover that information about how far we traveled, so about our position. And so again, if we we're ending here at 10 seconds. So if we jump the line at 10 seconds, then we know that this geometric shape is going to be the information we're going to recover. So this geometric shape is going to be the information that we recover about our changing position, or the way I ask it, how far did we travel? So if you think back, just to kind of pause here before we start the number crunching, if you think back to when we were giving you the function and having you find the derivative was that rate of change. And we know that rate of change was basically slope, right? I say derivative, you think slope. And we know slope is division, right? It's y over 1. So if we think about this reversal of this process, now we're multiplying, which is the reverse operation of dividing. So from a mathematical standpoint, it's very much the reverse operation. So let's go ahead and multiply out some dimensions here to get this area. So this shape is a trapezoid. We do have a trapezoid equation. And if you're a big fan of geometry, maybe you remember it. What I prefer to do is look at rectangle plus triangle, and that will give us the trapezoid. So I'm going to rearrange my calculation so that I have a rectangle that has a base and a height. And I have each one here, a subscript here, because this height refers to the height of the rectangle. And then I'm going to have to add to it the triangle, which has its own base. It happens to be the same as the rectangle in length, but it definitely has its own height here. It's different than the green region. So I labeled it H2. And so if we find our regions now, our regions, our base is 10 seconds, our height is 40 miles per hour. That's our rectangle. And then let's bring in our triangle. So half base times height, base of 10 and a height of 20 miles per hour. So, normally we would say multiply all that out and get a numeric answer, but we have a mismatch in the units here. We've got seconds and hour, and we know those units of time need to cancel, okay, in order to recover that information about position. And they can't cancel if one's a seconds and one's an hour. So there's a couple of ways we can approach this. We can convert our time into hours. We can convert our speed into seconds. But we can actually do something that's kind of slick. We can numerically find out what this answer is first. So I'm going to multiply this out. I get 10 times 40, that's 400. And I get half 10 times 20. So think about 10 times 20 is 200, half of that is 100. So 400 times, plus, 100. That's 500. Now what are my units? It's miles and seconds per hour. So I'm going to take the units of time and make it its own fraction. So I have miles, but I know I need to end up with miles. Miles times seconds per hour. This is where I'm going to do my conversion. It's kind of slick because you only have to convert one thing. So I'm going to multiply by that conversion factor to get me from seconds to hour. Now I need to cancel my units, which means I need seconds on the bottoms and hours on the top. So I'm going to multiply by 1 hour. I could have put 1 here. I guess I really should have. 1 hour is 3,600 seconds, right? We've got 60 seconds in a minute. That's 60 minutes in an hour. And now my units will cancel. My hours cancel, top and bottom. Seconds cancel, top and bottom. I'm left with miles. And my answer is 500 over 3,600. Well, we can reduce that. We can divide by 100 on top and bottom. And we have 5 over 36, 536 miles. So that is how far I've traveled in that 10-second interval as I slowed down from 60 miles per hour before the let's take a look at this one. I really modified this question because now I'm talking about a squirrel. But it's kind of the same idea. I just want to incorporate something a little different in each type, right? We had just a flat rectangle, really straightforward. Then we changed the shape up a little bit because our velocity was changing. Now the squirrels are kind of crazy, right? They run all over the place. So we have a squirrel running down the sidewalk, and he's running for 10 seconds. So what does the squirrel's velocity graph tell us about the squirrel's motion? So 10-second interval. When I do anything about velocity, it'll come. I'm going to count by twos on the y-axis, 2, 4, 6, 8, 10. And so this time is in seconds. We know that from the problem. We're measuring the squirrel's velocity in feet per second, FPS. And I'm going to have the squirrel do something like that. So what does that mean? If this is our rate of change function, we need to recover something about the squirrel's position. What does that rate of change function mean? Well, we know that from the previous two examples, that when we have a function up here in the first quadrant, we ended up a positive displacement. We end up with a positive distance traveled. So what happens when my velocity is negative? Well, that just means the squirrel turned around, right? We have go from positive velocity to negative velocity. Maybe we call that from, running away to running towards or something like that. And so we know that at this point, it's probably like 4 seconds, the squirrel turns around and the squirrel starts running back towards you, or starts running back towards you. And then here at 6, 7, 8 seconds, the squirrel changes its direction again. So it's running down that sidewalk back and forth. Okay, so we know the squirrel changes its direction. We also, if we're going to call this running away, then this is going to be running towards, and then the squirrel's going to change direction and run away again. So it's going to be like away and towards and away. Squirrels do that, right? Okay, so we can. The other thing we can could determine is that because these are curves, so this is also a little different from previous questions, because this is a curve and somewhat smooth, we can really only approximate. There's no geometric shape that we have that we can find an exact formula for. So we can only really approximate by, calling this close to some sort of shape. I'm not quite sure what we should use there, but we can make a good educated decision as to what to use. So let's start making those decisions. Let's just say that we're going to call this somewhat triangular. Now, this approximation in green here doesn't capture the entire area under that curve. And really what we're looking for is we're looking for the region between the curve and the horizontal axis. And that's pretty important, especially for these sort of scenarios. So that is the region that we're concerned about. And so this triangle really doesn't capture the entire region. It's a little bit of an underestimate, so to speak. But that's okay. We'll compensate for that somewhere else in the curve. How about calling this region here for 4 to 8 seconds where the squirrel is running back towards us? Maybe it's somewhat rectangular. And this, because this goes outside this region between function and the horizontal axis, is a bit of an overestimate. So maybe these two compensate for each other pretty nicely. And then this last section looks pretty darn triangular, still a little bit of an underestimate. But all three together, I think, would get us pretty close. So it's a matter of then finding those regions. So to find the distance, and really, we can really remove the word distance and really talk about displacement. And I'll talk about that in a second. So this first region was half base times height. I gave it the subscript 1 again because this base and this height may or may not be repeated anywhere else in the problem. And then this orange rectangle is going to be base times height. And again, it has its own base and its own height, so I'll give it the subscript 2. And this last triangular region 1 half base times height, again, its own base, its own height, so I'll give it subscript 3. And so let's go ahead and fill in the information. So this first triangle has a base of 4 and a height of 8, looks like. And we have seconds and feet per second, so we've got good compatible units for unit conversions. This rectangular area has a base of 4 and a height of 4, because remember we're counting by 2's on the y-axis. And this height is negative. So when I talked about this squirrel running back, or just changing direction, then we know that the squirrel is really the distance between me and the squirrel is decreasing because the squirrel's back to me. And then the squirrel changes direction again, and 1 half base times height, that base of 2 and a height of 6. And the squirrel turned around and started running away from me again. So after we do this, let's see what we have here. We've got 32, back 32 is 16, but then we've got negative 16. So what does that mean? Well, that means the squirrel ran 16 feet away from me and then came back 16 feet. So the squirrel came all the way back to me. And then the squirrel ran away again, looks like another 6 feet, right? Back to 1 times 6 is 6. So the distance then, or what we really should say is the position, is that the squirrel is 6 feet away from me. And so when we have, because this is the unique one where we change direction and our position starts coming back towards our original location, we don't really talk about distance anymore. The best scenario would be displacement. And I think I really should have the word displacement right there. In fact, I am actually going to stop the presentation and do that. I'm going to write this placement. I think that's a more accurate description We can distance is okay when they're all in the positive world, but we are not all in the positive world on that problem. So hopefully that, I gotta do all this again, but hopefully that adjustment plan will reinforce to you that you need that verbiage instead of the verbiage distance. So I know I'm probably doing a little spin with my time here, but why don't you just do this X through there? And that will, again, it will reinforce that even though we're starting out with that verbiage, that verbiage really is only for the that verbiage is really only for the most basic of cases when you're dealing with all positive velocity. Displacement is the more appropriate term that we're going to use from here on out. Okay, so important characteristics of the which we have. Graphing, we are graphing a rate of change. So we are graphing the derivative. We have a region that is between a function and a horizontal axis. So that means if I look at the function, I got to find a horizontal axis, and then I need to draw a vertical line to replace the shape. The answer represents a change in the value. Okay? So I can't stress this enough. Using this is really the basis of the rest of the year. Okay, when we start looking at these regions, we are representing a change in a value. With each one of the examples we just did, it represented a change in position, which is very well discussed. Okay, because it happens over time in the world. I started here and here. This is how far I moved. This is my displacement. And the units are super important. That's where we get our contextual information from. So multiplying those units, that's the reverse process of what we're doing before this. Okay, so here's a problem that I would like to try and learn. It's a drone, it's resting on the ground, it's kind of like the squirrel problem. It starts its ascent, and its velocity is in feet per second, so its velocity is in feet per second. And changes as indicated by this velocity graph, and the time is in seconds. So if you pause the video and go ahead and try this one on your own and answer these two questions. And then you can start the video up again and see the solution. Okay, so I'm assuming you've tried this on your own. So we know that this region represents a positive displacement. We're starting at the ground, so we can call the ground, if it says so resting on the ground, we can call that a position of 0. And so when we find the value of the area of this region, we have that base times height. The base here is 8 seconds. The height is 40 feet per second. And that's in feet per second because that's what the clock said. And so that ends up being 160 feet up. I'm calling it the altitude here, so I'm kind of getting rid of this generic distance terminology and start calling it an altitude or displacement. So we moved 160 feet up. Okay, and then it says what's its altitude after 16 seconds. So now we have to consider all of this movement all the way to here. So we know the first half. Let's figure out what's happening in the second half here. We know that second half has a negative velocity. So in this portion of the motion, again, it's a triangle. It's half base times height, but a base of 8 and a height, maybe the altitude of the height is down to the peak of the triangle. So that looks like negative 20. So 8 is negative 20. So we have the drone is dropping 80 feet in its altitude. So that drone is starting at the ground, up 160, and then drop down 80 feet. And so the altitude after 16 seconds then is taking this number and adding them together, right? Because one is negative. And when we do that, we end up with the final position for the drone, and that is that the drone had an altitude of 80 feet. Okay, so here's another problem. It requires you to approximate. And again, I want you to stop the video and try this one on your own. And then we can start the video and see the solution, see if you've got the right answer. Okay, if you're tuning in again, I'm assuming you've tried this on your own. So we have a velocity graph here. We see that it's a full shape, so we know we're going to have to approximate. And it's telling us right there, which answer down below here is the best estimate of the distance traveled. We can call it distance traveled because our velocities are positive, so it's okay. And so the car is traveling for 8 seconds, time is in seconds, velocity is in feet per second, so all the units are good. And I'm going to approximate this by just drawing a triangle. So there is what I'm going to approximate. Now, we will talk about whether that's a good or a bad approximation in just a second. But let's find this answer. Okay, so the distance here is half base 10. I have a base of 8 and I have a height of 50. So half of 400 is 200. So I shouldn't say altitude. It's a 5. Definitely not altitude. That's a typo. I'm changing it. Bear with me here. You can definitely call that distance. We're dealing with a positive velocity. So I'm changing the direction. Okay, there we go. The distance of 200 feet. So the next question is, well, that's not any of these answers. So the question is it 180 or is it 210? And this is where the best estimate portion comes in. So when we look at what we use to estimate here, we really aren't going to get an exact answer. So we have to take a look at where we compensated. So if we look at the first 4 seconds here, this first 4 seconds, this is actually like a little trapezoid, right? Well, we definitely underestimated by a significant margin here, right? So this is definitely significantly small. And then if you look at the last last 4 seconds here, we have this triangle. And this triangle represents an overestimate, right? We have this space outside the function here. It's not between the function and the x-axis anymore. And so this represents an overestimate, but this overestimate doesn't seem to be as large as this underestimate. So all things considered, it's probably closer to 180. It's just under 200 because we left a significant chunk off and we included just a tiny slip. So, I take it back. I explained that totally wrong. This is our approximation, and we left off a big chunk here. Sorry about that. We left off a big chunk here, and we included just a tiny sliver in that approximation. So we probably have some space that we didn't account for. So the actual area should be bigger because of all of this left over. That would be much bigger than this tiny sliver that we included that overestimated. So the answer then is going to be D, with cars traveling 210 feet over this 8-second period. Okay, so when we get into class, we will go over the takeaways from the notes and then do the, I think we have a circuit on this one. So we're going back to the circuits for just a day or so. So we will do those when we meet in class.